material selection, and characterization techniques. In the field of materials technology management, the processes of material selection and characterization stand as pivotal pillars governing the success and innovation of engineering applications. This guide aims to provide students with an in-depth understanding of how to strategically approach material selection for industrial applications and how these decisions are intertwined with advanced characterization techniques. Material selection. Importance of material selection. Material selection is a crucial process that influences the performance, durability, and sustainability of products. The right material can enhance functionality, decrease production costs, and ensure compliance with environmental regulations. It directly impacts a product's life cycle as well as its physical and mechanical properties. For instance, in aerospace applications, weight and strength are paramount. Thus, material selection must prioritize those characteristics to optimize fuel efficiency and safety. Approaching material selection. When approaching material selection for specific applications, a systematic and methodical process is required. The following steps outline a structured methodology. Define requirements. Clearly articulate the functional and operational requirements of the application, including mechanical loads, environmental conditions, regulatory standards, and life expectancy. Identify selection criteria. Develop specific material selection criteria based on the requirements identified. This includes considering mechanical properties. Example, tensile strength, ductility, physical properties. Example, thermal and electrical conductivity, chemical resistance, cost, and sustainability factors. Candidate materials listing. Compile a list of potential candidate materials that meet the established criteria. This process may involve consulting material databases, existing literature, and previous industrial applications. Shortlisting candidates. Utilize tools like Ashby charts to evaluate and narrow down the materials based on their properties in relation to the defined criteria. This visual representation allows for a comparative analysis of materials, focusing on weight, strength, and cost effectiveness. Evaluation and testing. Conduct experimental testing on shortlisted materials to evaluate performance against specific criteria. This may involve mechanical testing, environmental assessments, and compatibility tests as necessary. Final selection. Select the most suitable material based on comprehensive analysis and testing results. Consider factors like source availability, cost of manufacturing, and the potential for recycling. Examples of material selection. Aerospace industry. The selection of materials for aircraft structures has evolved significantly. Aluminum alloys are traditionally favored for their lightweight properties, with the aerospace sector increasingly integrating carbon fiber reinforced polymers to achieve a higher strength-to-weight ratio. For example, the Boeing 787 incorporates over 50% composites in its structure, improving fuel efficiency while maintaining performance standards. Automotive industry. In automotive applications, the shift towards lightweight materials has driven the adoption of advanced high-strength steels and aluminum. The Ford F-150, for instance, has transitioned to an aluminum body to reduce weight significantly, which enhances fuel efficiency without sacrificing safety or performance. Material characterization. Importance of material characterization. Material characterization is indispensable in understanding a material's properties and behavior under various conditions. It provides critical data that influences both material selection and performance predictions, ensuring that materials are fit for their intended applications. Effective characterization can identify potential failures, enhance product reliability, and facilitate compliance with industry standards, but Key material characterization techniques. Several techniques can be employed to characterize materials, each with its advantages tailored to different property assessments. X-ray diffraction, or XRD. This non-destructive technique is used for determining crystal structure, phases, preferred orientation, and other structural parameters in crystalline materials. XRD is essential for assessing material quality and phase composition, which directly influences performance. For example, XRD is widely used in the aerospace industry to determine the phase stability of metals and alloys used in critical components. Scanning electron microscopy, or SEM. SEM offers high-resolution imaging of material surfaces, enabling detailed examination of microstructures and defects. This technique is invaluable for analyzing failure mechanisms, wear patterns, and surface morphology. For instance, SEM analysis in automotive manufacturing allows engineers to study fracture surfaces of components subjected to high-stress conditions. Thermal and mechanical testing. Techniques such as differential scanning calorimetry, or DSC, and tensile testing provide insights into thermal properties and mechanical strength, respectively. These tests help predict the material's performance in service conditions and can be critical in ensuring compliance with safety regulations. Applications of characterization techniques. Aerospace case study. In the development of advanced composite materials for the Airbus A350, XRD was utilized to analyze the crystallographic phases and thermal stability of resin matrices during different processing conditions. This characterization helped optimize the curing processes, ensuring the reliability of the final product. Automotive case study. Diesel particulate filters in automotive applications are characterized using a combination of X-ray fluorescence and SEM. XRF identifies the elemental composition, while SEM provides insights into the microstructure that affects filtration efficiency, guiding the material selection for improved performance. Integration of material selection and characterization. Importance of integration. The integration of material selection and characterization processes fosters a systematic approach to materials technology management. When material selection is informed by thorough characterization, it significantly reduces the risk of performance failures and promotes innovation in material use. This symbiotic relationship ensures that materials are not only suitable for their applications, but also capable of sustaining the demands placed upon them during their life cycle. Strategies for effective integration. Feedback loops. Implement continuous feedback between the selection and characterization stages. Data obtained from characterization should inform future material selections, creating a responsive material design process. Collaborative approach. Encourage collaboration between material scientists, engineers, and designers. Cross-disciplinary teamwork enhances understanding of material properties and application requirements, leading to well-informed decisions. Utilization of software tools. Leverage computational tools that integrate material data, enabling simulation and prediction based on specific material behavior. Such tools can facilitate quicker selection processes while ensuring compatibility with design specifications. Training and education. Provide ongoing training for engineering teams on the latest characterization techniques and their applications in material selection. This promotes a culture of knowledge sharing and adaptability within organizations. The processes of material selection and characterization are essential components of materials technology management. A systematic approach to material selection ensures that effective decisions are made based on empirical data derived from rigorous characterization techniques. By understanding the interplay between material properties and application requirements, students and professionals can innovate and enhance product performance across diverse industries, including aerospace and automotive manufacturing. Embracing this integration not only leads to better materials but also paves the way for sustainable and technologically advanced engineering solutions.